Hi everyone, and welcome to another mini course at Physics Latam. Today we are happy to have Professor Mark Gross, who will give a series of 5 lectures about his work and the Gross-Siebert program. He obtained a PhD in the 90s from the University of California. His supervisor was Professor Robin Hashron. From 90 to 93, he was an assistant professor at the University of Michigan and spent the academic year 92-93 on leave as a postdoctoral researcher at the Mathematical Science Research Institute in Berkeley. He was at the Cornell University from 93 to 97 as an assistant professor, and in 97 to 2001 as an assistant professor. And then from 2001 to 2013, at University of California as a full professor. Since 2013, he was professor at the University of Cambridge, and he still is. And since 2016, he's a fellow of the King's College, Cambridge. Work on complex geometry, algebraic geometry, and mirror symmetry. Gross and Gross-Siebert develop a program known as the Gross-Siebert program for studying mirror symmetry within algebraic geometry, which is the topic of this mini course. Professor Gross has won several distinctions. In 2016, Gross and Siebert jointly received the Clay Research Award. In 2017, Gross was elected a Fellow of the Royal Society. He has written many fundamental papers in algebraic geometry and mirror symmetry, and also famous textbooks like Tropical Geometry and Mirror Symmetry, on Calabi-Yau manifolds and related geometry with Dominic Joyce and Daniel Hubrecht, and my favorite, Dirichlet Friends and Mirror Symmetry, which is co-authored with several amazing physicists and mathematicians, and many more important work. It is an honor to have him with us today and to give us this series of lectures. Thank you very much for accepting our invitation.
Thank you for the very kind introduction. That's lecture 1, introduction to mirror symmetry, and subtitle is a biased history. Since I will certainly not hit on many points that have been developed over the last 30 years. So the starting point of this story really comes from definition of Calabi-Yau manifold. So I'm not sure if you will have seen this in some of the other lectures, but these are fundamental objects from the point of view of string theory because they provide good compactifications for superstring theories. So for us, this is a compact n-dimensional complex manifold with a nowhere vanishing holomorphic n form. Omega. So locally, if you have Z1 to Zn complex coordinates, you should be able to write omega as some holomorphic function of Z1 through Zn, which is nowhere vanishing. So locally, times dz1 wedge dot 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 wedge dzn. And so that's nowhere 0. Now, usually we'll be assuming that the Calabi-Yau manifold carries a Kähler metric. Okay, and why might one, as a physicist, care about these things? In particular, Calabi-Yau threefolds, three-dimensional Calabi-Yau threefolds provide compactifications of superstring theory instead of working with, say, the space-time, which is 10-dimensional with signature 1,9. Instead, you can work with ordinary Minkowski spacetime, 4-dimensional spacetime cross a 6-dimensional, so real 6-dimensional Calabi-Yau threefold, which is 6 real dimensions. Now, I emphasize I'm not a physicist, so I think this is the limit of the physics I'm going to actually say in these talks. Okay, so one of the crucial bits of information about a Kähler manifold are its Hodge numbers. So these are what is HPQ of X, and this is the dimension. There's a couple ways this is written. I'm going to assume you've seen this before. The dimension of the PQ Topological cohomology group. Or if you want, dimension of Q cohomology, sheaf cohomology group of the sheaf of holomorphic P forms. Okay. So if you have a Calabi-Yau threefold, X, let's assume also X simply connected or finite fundamental group. That implies that, in fact, quite a few of these numbers are zero. H10 of X is 0, and H20 of X is 0. And finally, H30X, which is the space of holomorphic three forms, is one-dimensional. So typically, you put all of this information into what's known as the Hodge diamond. So this looks like, I'll just draw a bit of this, H00, H10, H01, H20, H11, H02, etc. There are certain symmetries that these Hodge numbers have, and in particular in the case of this Calabi-Yau threefold, with these properties being simply connected or finite fundamental group, the Hodge diamond looks like this. So you have H00 is always 1. You have zeros here, so H10 and H01 is 0. H200, you have some number, H11, and by general symmetry properties, the Hodge diamond will be symmetric around the vertical axes here and also around the horizontal axis, which is the horizontal axis about the middle row, which is this row. And so the next row is H11, 0, 0, 0, and 1. Sorry, that got a bit small. So there's a symmetry about the vertical axis and about this axis here. So there are really only two numbers you have to worry about when you're talking about a Calabi-Yau threefold, either from this information here or from the symmetries. Okay. So just perhaps as a note, the topological Euler characteristic of X has a very simple form here. It's just 2 times H11 of X minus H12 of X. Okay. Let's look at what will be one of our standard examples. Let's take the quintic threefold. This is perhaps the most famous example. So X is given by the set, the equation, take a very specific equation, x0 to the fifth plus dot 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 plus x4 to the fifth equals 0. So the set of all points in P4 satisfying this equation in complex projective 4 space. So this, you can compute the Hodge numbers of this. This is a Calabi-Yau threefold. And H11 of X, that is easy to calculate as being 1, and H12 of X is 101. Okay, so these numbers can actually get pretty big. Now, there were two hints initially of what turned out to be called mirror symmetry. So I'll mention the first one, is the Green-Plesser orbifold construction. So if we take this particular quintic threefold, so this is going to give the mirror to the quintic, or the mirror quintic. Then what Green and Plesser observed, looking at symmetry, so again, I'm going to wave my hands at the physics, but essentially what Green and Plesser did is they looked at some symmetries of what they believe is the conformal field theory associated with this Calabi-Yau threefold X, and saw that if you divide out by a certain group of symmetries, you get something now, the conformal field theory, which appears to be, quote, the mirror. I haven't defined mirror yet, so put that in quotes. So they then emulated the conformal field theoretic construction in geometry, and this is what they got. So consider the subgroup Z5 cubed sitting inside, or maybe I should write this as Z5 to the fourth, mod Z5, sitting inside Z5 to the fifth, mod Z5. That's a subscript. So here, this is the subgroup consisting of tuples A0 through A4 with AI in Z5 and summation AI equal to 0. Then we divide out by the diagonal subgroups of the set of things that form AAAA with A in Z5. Okay, so this, there are 4 degrees of freedom with the AIs, because once you know 4 of the AIs, you know the 5th. So the numerator here is this group Z5 to the 4th, and the denominator is the diagonal Z5. Now, this group will act by multiplying by roots of unity on the points in CP4. So let's call this group G, and A0 through A4 in G acts on CP4 by a point in CP4, X0 through X4, maps to C to the A0, X0, through C to A4, X4, where C is a primitive 5th root of unity. So where C is equal to, say, e to the 2 pi I over 5. Okay, so this acts on CP4, so we have a group action of G on CP4. Notice the reason why we divide out by this Z5 is that the diagonal action, that just multiplies rescales every coordinate by the same amount. And since in CP4, any 2 points whose coordinates are just differed by a common factor represent the same point. Okay, so that's the group action. Now, the other thing to note is because we're just multiplying these coordinates by some 5th root of unity, this equation, if a given point satisfies this equation, then it still satisfies the equation after multiplying the coordinates by some fifth roots of unity. So G acts on X. And we have a quotient X mod G. Okay. Now, the trouble is that X mod G is very singular. G, the action of G has a lot of fixed points, and you need to do something called resolution of singularities. There exists a resolution of singularities. I'll write it X hat to X mod G. So in other words, what does this mean? So this map is, well, it's proper. It's an isomorphism away from some dense open set. Sorry, it's an isomorphism on a dense open set of X mod G. There's a resolution of singularities. X check is non-singular. And as a fact is a Calabi-Yau manifold. Now, that's not an easy statement. The combinatorics was quite imposing when people first started looking at this. But it wasn't, it was shown fairly quickly that, in fact, X check has the following property. H11 of X check is equal to 101, and H12 of X check is equal to 1. Now, well, let's just compare that with what we had. You can see that that interchanges these two. So what's happening is we're interchanging H12 and H11, and we're getting a symmetry about this axis. We're flipping the Hodge diamond around this axis and getting the Hodge diamond for another Calabi-Yau threefold. And that is, as my understanding, is the origins of the word symmetry was this reflection about the axis and the Hodge diamond. And in fact, a different work, so Candelis, Linker, and Shimrek, also classified Calabi-Yaus in weighted projective space. So this is a generalization of ordinary projective space. And found that there were many, many pairs which interchange the Hodge numbers. Now, there's a famous plot which I want to show you. Just find the plot here. I just seem to have lost it here. I had this set up earlier. The page seems to have shifted. There we are. Okay. So what this plot shows is many examples as a scatter plot. The axis of the bottom is the Euler characteristics. That's the difference of the Hodge numbers times 2, whereas the axis, the vertical axis, is the sum of the Hodge numbers. So if you interchange H11 and H12, you're going to change the sign of the Euler characteristic, but of course the sum of H11 and H12 is the same. So here's Euler characteristic 0 at this point here. And you're reflecting what you see as a symmetry about the vertical axis. So here you see many, many examples of Calabi-Yau threefolds, and they seem to come in pairs with H1 and H2 interchanged. So that was the beginning of the story, was this observation that Calabi-Yau seems to come in pairs. And furthermore, there seem to be some natural reasons that this should happen from the conformal field theory point of view. But again, that's beyond my competence to really talk about. So this was already sort of something unknown to mathematicians, because mathematicians hadn't been working so hard to classify Calabi-Yau threefolds at that point in time. We didn't actually know that many examples. But really the most important bit of early work was work with Candelis, Laosa, Green, and Parks. That's a different Green Plesser. It's Green without an E. And they carried out calculations of the so-called UKol couplings. And again, this is not something I'm going to go into detail on. This is just for historical purposes. For the quintic and the mirror quintic.
Can I add something?
Yeah, of course.
We recently have a talk by Xenia de la Osa, which she explained the history of all these Chicago couplings very in detail. So people who might be interested in this part of this physics part, they can check this talk.
Okay, good. Okay, so this will not be completely out of the blue. Okay, so there are two different sorts of UKol couplings, and these were done, so different UKol couplings were computed for the mirror quintic and the quintic, but they're supposed to, under mirror symmetry, there's two different sorts of UKol couplings are supposed to be interchanged. So for the mirror quintic, these couplings involve what are known as period integrals. And I'll refer to Xenia's talk for much more detail, but let me just say sort of the crucial bit of information on things of the form integral over 3 cycles, the homomorphic 3 form. And this would be the homomorphic 3 form on X check. And this is a 3 cycle. Now I'm hiding a lot here. You have to look at how these periods vary as the complex structure in X checker is in one primer family. But there's some magic you can do, and you can extract some power series from these. So on the other hand, on X, we obtain the number of rational curves. This is something I'm going to make a bit more precise, or much more precise as the talks go on. Number of rational curves of degree D on X. So for example, N1 is the number of lines on X, which can be slightly dishonest and claim is 2,875. N2 is the number of conics on X, and the answer is 609,250. And N3 is the number of twisted cubics on X, which is, I'm not going to keep on writing these numbers, but just to give some feeling to the fact they get complicated and big quickly. And again, a fun little bit of history here was the Candelis et al. Paper had these numbers. This was classical. This was 19th century. done by 19th century mathematicians. This was done by Sheldon Katz in 1986. This number was obtained by mathematicians, Elmsrud and Stroma, around the time, sort of simultaneously as the work of Candelis et al. The thing is that this was a difficult computation mathematically, and they actually got a different answer. So there was some discussion of who was right. Mathematicians couldn't understand the physics side of the story. But then it turned out that there was a bug in Elmsrud and Stroma's computer program, and once they fixed it, the numbers agreed perfectly. So the physicists were right. So this was quite striking. I still remember when I first heard about this as completely mysterious calculation done on the mirror side. It has nothing to do with enumerative geometry, the geometry of counting, things like lines and conics. And nevertheless, they were able to get predictions for all these numbers. And when I write ... this was the limit of our knowledge mathematically. They got a generating function for all of these numbers for any degree. So it was looked like a huge step forward. So what I would say is the driving mystery from the point of view of mathematicians is, why does this work? Okay, so that is kind of, for me, the end of the physics story that I'm going to be telling. And now I'm going to give you various landmarks along in the development of the theory in the mathematical world. So the next topic, I would say, is the battery construction. Of mirror pairs. And I thought I would actually, even though this is 30 years old, this was 1993, I'm going to explain this in some detail because I need to introduce toric geometry, because it's going to sort of lie at the foundations of what I do later. So I want to take the time to develop toric geometry properly. So we're going to have a little aside here where I will talk about toric varieties. So these are a particularly nice set of algebra geometric objects of varieties, which are determined entirely by combinatorial information. So the basic setup here is always going to be the same. We have some lattice n, so n is z to the n, just in Abelian group, z to the n. And then we have the dual lattice, z n set of homomorphisms from n into z, which of course is also z to the n, but I don't really want to think of these as being dual. And then we also have corresponding vector spaces, so with this n tensor z r, or if you want just r to the n, and mr is n tensor r, again isomorphic to r to the n. Okay, now the fundamental combinatorial object is what we call a rational polygonal cone. And this will be a subset of NR, is a subset sigma contained in NR, where I can write sigma as sum of positive linear combinations of some set of MIs with M1 up to MS being in M. So this just means the set of all things that form AI MI with AI I equal 1 to S with AI greater or equal to 0. Okay, so this is so M1 through MS are called the generators of the cone sigma. Okay, we also say the cone is strictly convex. If sigma intersect minus sigma just consists of zero. So the only point of sigma such that minus it is also sigma is zero. Okay. And generally we'll be interested in strictly convex cones in N. Now there's a dual cone. Sigma dual is defined to be the set of all N in MR such that M evaluates positively on N. So here I'm thinking of, there are various ways you might want to write this. If you think of M as a linear functional, this is the linear functional N evaluated on the point N. So we have N evaluated on N should be positive or non-negative for all N in sigma. So it's just the set of linear functionals which are non-negative on the cone sigma. And then I have a more discrete object, P sigma, which is defined to be sigma dual intersect the group M, the lattice M. This is what's known as a monoid, is a commutative monoid. I.e., we can add elements of P sigma to get an element of P sigma. And 0 in P sigma is the additive identity. So monoid is like a group, except that inverses don't necessarily exist. If M is in P sigma, minus M may not be in P sigma. Also, I'm not going to repeat the word commutative, but it's obviously commutative because addition in M is commutative. So monoids are going to play a crucial role as these lectures go on, and they'll always be commutative. Okay, so let's sort of do a few quick examples. Take sigma 1 to be just the first quadrant. So this is the cone generated by 1, 0, and 0, 1 sitting inside R2. Then sigma 1 dual is also the first quadrant. Not very interesting. But P sigma 1 is just the integral points in the first quadrant. So something like that. Draw the outline there. And I can write this as the monoid N squared, where N is the monoid. It's the natural numbers, including 0. So this is the simplest example of a monoid. It's just the set of positive, non-negative natural number, non-negative integers. Okay, so there is one example, very simple example. Let's look at a second example. Let's take sigma 2 to be cone generated, again, in 2 dimensions, cone generated by 1, 0, and 1, 2. Looks something like that. The dual cone now is a little bit more complicated. The dual cone, you can work out, and if you haven't done this sort of thing, I definitely recommend it as a homework exercise, is generated by 2, minus 1, and 0, 1. As you can see, 0, 1, for example, takes the value 0 on this generator and takes a positive value here. So 0, 1 is positive or non-negative everywhere on sigma 2. Similarly, 2 minus 1 is 0 on 1, 2, and is positive on 1, 0. So those are one of the boundaries, generated boundary rays of the dual cone. Now, P sigma, if I were to draw P sigma, that would look something like well, I have the point 0, 1. I have all of the positive quadrant points, but I also have over here, I have 2, -1, I have some more points here. I'll draw a dotted line for the outline of the cone. And notice that the point 1, 0 is not an integral linear combination of these two. So 1, 0, or this plus this is twice this. So specifically, I can write P sigma 2 as a monoid generator with 3 generators, A, B, and C, subject to the relation that A plus B is equal to 2C. And here A corresponds to 2 minus 1, B corresponds to 0, 1, and C corresponds to 1, 0. So you can see then that if I add A and B, I get 2, 0, which is twice C. And that's the one relation. It turns out that there are no further relations in this monoid. So the first example is what we call a free monoid. It just has 2 generators with no relations. This monoid has 3 generators with 1 relation. And of course, it can get more complicated. Okay, so what do we do with these rings? So, these monoids. So we have the notion of the monoid ring. These monoid rings. So if P is a commutative monoid, and again, as I said, I'm going to leave off the word commutative, so it's just be monoid. We have the associated monoid ring, which I will write. So I'm always going to work over the complex numbers. So I'll write this as C bracket P. This is direct sum over all elements of the monoid of C times Z to the P. So this is just as a vector space, with basis given by these symbols Z to the P, where P ranges over all elements of capital P. But then we also define a product rule. I want to turn this into a ring with a product rule given by Z to the P1 times Z to the P2 is equal to Z to the P1 plus P2, where the addition is the addition rule in the monoid. Maybe I will just, to be clear, write this as P plus to indicate that I'm writing the monoid operation as plus. Okay, and then you can just find the full product on this ring by using the distributive law once you know this product. Okay, so for examples, C bracket, the monoid of natural numbers, that coincides with just an ordinary polynomial ring. So here Z to the P gets mapped to X to the P, where P ranges over elements, non-negative natural number, non-negative integers. C bracket N squared is isomorphic to C bracket XY, polynomial ring in 2 variables. Again, Z to the AB here gets mapped to X to the A, Y to the B. And then you can see that this product rule is just the law of exponents for multiplying these things. And then my last example, so remember this was C bracket P sigma 1. That was the monoid associated with this cone sigma 1 I showed you earlier. That was this cone here. That was the monoid n squared. And now for P sigma 2, I have this description of P sigma 2 in terms of generators and relations. And in fact, this gives us a isomorphism. So C bracket P sigma 2 is isomorphic, and I'll draw the map the other way. It's isomorphic to C bracket X, Y, Z modulo X, Y minus Z squared. And here X corresponds to the generator Z to the A, Y corresponds to the generator Z to the B, and Z corresponds to the generator Z to the C. And this relation here is just really another way of writing the relation Z to the A, Z to the B is equal to Z to the C squared, i.e. A plus B is equal to 2C. So this polynomial relation that we see over here is really just the exponential, in a sense, of this additive relation on the generators of the mono. Okay, so this gives us a fairly rich way of describing some rings. But what we get in particular in general, given a strictly convex rational polygonal cone, we get sigma, we get P sigma and a variety or scheme. I believe you have had some exposure in the series to scheme language. U sigma, which is the spectrum of C bracket P sigma. So if you're uncomfortable with this language of spectra, then let me just point out, what that means. So, for example, the spectrum of this ring is really just the variety in affine 3 space defined by this equation. So, e.g., U sigma 2 is the zero set of the equation x, y minus z squared inside affine 3 space, so C3. Okay, so this is one way of cooking up some, not every possible variety, but some interesting range of affine varieties. Okay, so next, we're going to start putting these things together. So we'd introduce the notion of the fan. The fan, the collection sigma, of strictly convex rational polygonal cones in NR such that, first of all, whenever sigma is a cone sigma and tau is a face of sigma, then tau is also in the collection sigma. So, of course, face, I hope, is intuitively obvious what that means. So, for example, with this cone sigma 2, the faces of sigma 2 are sigma 2 itself, this ray, and the vertex of the cone. Those are the four faces of sigma 2. So the second thing we need is that whenever sigma 1, sigma 2, and sigma, and sigma 1 intersects sigma 2 is a face of both sigma 1 and sigma 2. So what this says is that essentially these cones have to fit together snugly. So for example, in R2, we have the following fan. We have 3 two-dimensional cones, and here I'm going to take generators to be 1, 0, 0, 1, and -1, -1. We have 3 two-dimensional cones, 3 one-dimensional cones. Those are these cones, and then 1 zero-dimensional cone. Now, to just do a slightly simpler example, in R, we have the fan. There aren't that many examples of fans in R. This is the only fan which in R which completely covers R. Okay. Now, the key point is, why do we like fans? So if tau is a face of sigma, turns out that U tau is naturally an open subset of U sigma. So if we have, well, maybe I'll do a specific example. So for example, let's consider this fan. And this is about as simple as things can get. We have 2 cones, sigma 1, sigma 2, and we have the 0 cone tau. So sigma 1 corresponds to, well, sigma 1 dual is just positive axis, r greater equal 0, p sigma 1 is equal to n, and c bracket p sigma 1 is equal to c bracket x. And so u sigma 1 is just, well, it's just a1, the affine line, or if you will, it's a copy of c. Now sigma 2, the dual cone, is minus r greater equal to 0. That's the negative axis. And I can write p sigma 2 then as maybe being minus n, so the non-positive integers. And then it's convenient to think of c bracket p sigma 2 as being polynomials not in x, but in x inverse. It's still a polynomial ring in one variable, but I want to record this as really being negative powers of x instead of positive powers of x. And then the dual of tau, so that's 0. Everything is non-negative on tau, so this is all of r, and p tau then is just the integer z. And so we often write c bracket p tau as polynomials in x and x inverse. It's sometimes called the Laurent polynomial ring. It's like Laurent Taylor series, Laurent power series, but just finite. And u tau is just, it can be identified with, all right, this is c star, this is c minus 0. So what happens is that you get 2 inclusions here. You have u tau sitting inside u sigma 1 and inside u sigma 2. But the way to think about this is that U sigma 1 throws the origin in to C star. So U sigma 1 looks something like this. U sigma 2 looks something like this. And U tau is just a copy of C star, which can be viewed as identified with A1 minus the origin. So U tau is equal to U sigma 1 minus the origin, and is equal to U sigma 2. I want to think about it as U sigma 2 minus infinity, because of course X inverse is 0 at infinity. Okay, so now what we can do is we can glue together U sigma 1 and U sigma 2 along this open subset. So glue U sigma 1 and U sigma 2 along U tau. And what we get is CP1. Because the description, these U sigma 1, U sigma 2 are the two standard affine open subsets of CP1. One where we remove if you think of the CP1 as a Riemann sphere, one of these open sets we remove infinity, one we remove 0. So this gives a description of CP1. So in general, given an fan sigma, we can glue together all the U sigma, or sigma and sigma, using the natural open inclusions U tau contained in U sigma whenever tau is a face of sigma. Okay, so I'm not going to go through that much detail on exactly how that works. I strongly recommend that you play around with this a little bit. So let me give you two examples, which I'll leave as exercises, two-dimensional examples. If I go back to this example of three two-dimensional cones, then X sigma is equal to CP2. Each of these three two-dimensional cones will give you a copy of the affine plane, and then they get glued together as a way the three open affine subsets of CP2 get glued together to get UX sigma. So that's a very good exercise to do for this. And then here's a slightly different one. I'm going to just take this. This is 1, 0, 0, 1, minus 1, 0, 0, minus 1. And in this case, you can try to convince yourself that the corresponding variety is P1 cross P1. So in general, we get this lovely correspondence between these purely combinatorial objects, namely fans, and certain kinds of varieties. Not every variety can be expressed this way, but the great advantage of this is you can read off a lot of information about the variety from the combinatorics. Okay, so that is a very brief introduction to the theory of fans. Now, in fact, there's another way to try to describe toric varieties, only projective toric varieties, though. And this actually is a little bit simpler. I was thinking of doing this first or only doing this, but there's a good reason later on in the lecture series to talk about fans at this point. Sorry, I should say projective toric varieties. Now, not every toric variety is projective. Maybe it's not compact already, but sometimes they're compact, but can't be embedded in projective space. So there's a different construction which always only yields projective torque. So here we're going to start with delta contained in MR. So notice this is the not N, but M. It's going to be a slight switch. We're working on the other side. It's a lattice polytope. And I'm going to define, so what's a lattice polytope? So i.e., the convex hull of a finite subset of it. So a typical example would be, for example, you take the set of points 0, 0, 1, 0, 0, 1, maybe 2, 2, and then the convex hull of this set of points is the polytope. It looks like this. In this case, it's a polygon. And the important point here is that all of the vertices are interval points or points in the lattice M. Okay, so now let's define the cone over delta. So this is C of delta, which is just a set of pairs MR and MR plus R. I add one dimension where I'd have R greater or equal to 0. That's just a real number. And M is an R times delta. In other words, I rescale delta by factor R. If R is 0, that means M has to be 0. I rescale delta, and M has to lie there. So what this looks like, I'll just draw this here, is this whole polygon is put at height 1 in the three-dimensional vector space. And then we take the cone generated by that polygon. So it looks something like that. Okay. And then I'm going to find corresponding monoid. Let's let the P delta be the integral points of the cone delta. So we intersect with M plus Z. And now we take the ring, the monoid ring, as before, over P delta. So notice there's no dualizing this time, which is why I started working in M. I take the monoid ring C of P delta, and this is a graded ring. In other words, I have a notion of degree of an element with degree of a generator Z to the M R being R. So in other words, I grade, so the generator Z to the P of this ring, the P lies in some slice, some height slice here. So for example, the height 1 slice elements would be degree 1, but you might have higher height points in the cone. You will have higher height points in the cone. And that allows us to define the notion of degree. And of course, the product rule is homogeneous. Degree of Z to the M1 R1 times Z to the M2 R2 is degree of Z to the M1 plus M2 R1 plus R2, which is R1 plus R2, which is degree Z to the M1 R1 plus degree Z to the M2 R2. So this is an example of a graded ring. We have a notion of degree, and its degree respects products. And as such, we can take the proj of this. So this is, again, an algebra geometric construction. This time, I'll do an example in a second. Proj of C bracket P delta is the projective variety with homogeneous coordinate ring. C bracket P delta. Okay, so if you haven't seen the project construction, let me just do a few examples to show you in the situation we're dealing with is really quite simple. Let's do a few examples. The first in one dimension, I can take delta to be just the unit interval. So then the first thing I do is I take the cone over this. So I put this I at 1, think of this as being 0, 1, 1, 1, and I take the cone over this. And I take the integral points inside this cone. So the origin on this point, 0, 2, 1, 1, 2, 2, 2, and so on. And it's not too hard to see that this monoid, P delta, is now generated just by this element and this element. Everything inside this cone here is a positive inner combination of these two elements. The P delta is equal to n squared generated, so with generators. Um, 0, 1, and 1, 1. So for example, you can get 1, 2 by adding 0, 1, and 1, 1. Okay, so this is a graded, so C bracket P delta is isomorphic as before. This is just isomorphic to C bracket XY. And X and Y correspond to 0, 1, and 1, 1. So these are both degree 1. So this has the standard grading of polynomial ring in two variables, namely X and Y are both given degree 1. Standard grading of by degree of polynomial. And then proj of this is the homogeneous coordinate ring of P1. This is just another way of describing CP1. Okay, so this is another way of describing P1 using combinatorics, using toric geometry. If I take instead, I take the standard simplex, so now let's work in n dimensions. I take, say, Zn with the standard basis, E1 through En, and delta to be the convex whole of 0, E1 through En. So this will be one way of writing standard simplex. So for example, in 2 dimensions, this will just look like this. Then P delta is just n to the n plus 1, again generated by the height 1 copies of these things. And C bracket P delta, I can then write as C bracket X0 through Xn with the standard grading. And then, of course, proj of this is CPN. So this gives a very quick, efficient way in this language of describing CPN. Let me do one more example. Let's take m equals z2, and then I will take just the unit square. And in this case, it's not too hard to see. So again, you put this I1, take the cone. Turns out that the cone is generated by the height 1 integral point. So P delta is generated by, so let me write this as generators 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, but subject to a rather obvious relation that if I add, okay, let me just write it down, 1, 0, 1 plus 0, 1, 1 is equal to 0, 0, 1 plus 1, 1, 1. Right? These are both equal to 1, 1, 2. That's saying that essentially if I add this and this, I get the same thing as if I add this and this. So that's a description of the monoid, and Cp delta, C, the monoid ring, Cp delta is equal to C bracket X, Y, Z, W, with these generators corresponding to the four generators in monoid. And then I have to record this relation between the generators in monoid as a binomial. We divide out by the ideal. 1, 0, 1 corresponds to Y, 0, 1, 1 corresponds to W. So YW should be the same thing as XZ. So I have an equation of YW minus XZ. And so then proj of this, proj C bracket P delta, is the zero locus of YW minus XZ inside CP3. This is the quadric surface. Okay, so again, this time we've gotten a projective variety. And let me just give one example as an exercise. What does this polytope give you? Okay, so now really one of the most important points is that given this projective variety, given a projective toric variety coming from polytope delta, I can write down equations of hypersurfaces in that toric variety. So in particular, note an equation of the form the summation m in delta intersect m of am times z to the m1. So this is an element. This is a degree 1 element of C bracket P delta. And in particular, that makes sense as an equation and defines a well-defined hypersurface. Here, A sub n should lie in some elements of C. Finds a well-defined hypersurface. So, for example, in this case, I might be dealing with some linear combination, some equation given by ax plus by plus cz plus dw equals 0. That defines a linear hyperplane section, a linear section of the quadric surface. So such an equation defines a hypersurface. In the variety proj C bracket P delta, which I'm going to give the name. So this variety, this proj, I should give the name P sub delta. Should think of this as a generalization of projective space coming from the polytope delta. Okay, so whenever we have a homogeneous equation, namely one whose all of its terms are the same degree, it gives you a well-defined hypersurface. Okay, so now this was a long sideshow for discussing the Batarov construction, and now we're ready to get back to it. So Batarov's key observation was that certain hypersurfaces of this flavor, depending on the torics of delta, certain hypersurfaces are Calabi-Yau. And there was a simple characterization of such hypersurfaces or such toric varieties. So polytope delta is said to be reflexive.
Oh, hello.
Yeah.
Can I ask a question?
Yeah, of course.
So we did two constructions on how to construct a variety. In the second case was projective. Mm-hmm. But if I start from a lattice polytope, I can create a fan and then apply the first construction. Is there an kind of easy way to see that these give me the same variety or scheme?
So it takes a little bit of work, but yes, I should have talked about that because I've just given you two constructions and didn't say they had anything to do with each other. So maybe I should, let me just add a note here, and I don't want to, again, it's supposed to be able to move, there we go, okay. So let me add a remark. From a lattice polytope, delta, one can construct this normal fan. Which I'll write as sigma, and X sigma is isomorphic to P delta. So the toric variety coming from the fan is the same. Let me just do a very quick example. I didn't want to talk about this very much at all. I was planning to mention this, but didn't want to talk about it much at all because we won't really be needing it. So if you think about the inward pointing normals, think of the normal vectors as really living in the dual in N. We have some inward pointing normal vectors, and that gives us 3 rays. Now, if I then take at each vertex, I take the cones spanned by the normal vectors of adjacent faces, I will get, for example, at this vertex, I will get the all non-negative linear combinations of the 2 normal vectors. I get this cone. At this point, I would then get, I guess I would get this cone, and then at this point, I would get this cone. So I actually get a fan, which is called the normal fan, and then we get a correspondence between the projective toric varieties, P delta, and its isomorphic to X sigma. Once you're sort of sufficiently adept at toric geometry, it's all sort of fairly straightforward. But I don't want to take the time to explain one. But it's a good exercise if you want to spend a bit of time getting your head around all these things. Okay, thanks for that question. Okay. Okay, so polytope delta, so here's Batarov's definition. Polytope delta is reflexive if 0 lies in the interior of delta, and the so-called polar dual. So this is delta like that, delta dual like this. This is all set of all n in the dual vector space, such that m evaluated on n is greater or equal to -1 for all m in the original polytope delta. And what we require, I'll do an example in a second to try to unwind this. But what we'll require is that this is also a lattice polytope. So this is always a polytope, but it may not be generated by integral points. It may not be generated by points in M, but rather maybe the vertices are rational. So just by way of an example, here's perhaps the simplest example. We're going to take the convex hull of these 3 points. So that looks like this. So this is a lattice polytope. The vertices are all integral, and it has an interior point, which is 0. So that's delta. And then delta dual, it's not too hard to see that that is spanned as vertices -1, -1, -1, 2, and 2, -1. Certainly, lines aren't particularly straight there, but it's clear the origin lies here. And if you sort of think about this, so -1, -1, notice that takes the values -1 here, -1 here, and the values 2 here. So just by linearity, the value of any point in delta is greater or equal to -1 on this. And similarly, -1, 2 takes the values 2 here, -1 here, and -1 there. So again, it takes values at least -1 on this polytope, and similarly 2, -1. So you get actually an order reversing. The vertices here correspond to maximal faces here. So it's not too hard to see, anyway, along those lines, that this is delta dual, and this is, again, the lattice polytope. And just for reference here, I want to add a few more of these points. So we have, sorry, my lattice isn't so good here. Okay, well, my lattice isn't that even, but those are the integral points inside that polygon. Now, it's not too hard to see. So delta dual isn't quite the standard simplex that I showed you earlier, which gave rise to P2, but rather it's 3 times the standard simplex. And in fact, rescaling the simplex doesn't change the corresponding toric variety. Delta dual is 3 times standard simplex. But rescaling does change what you think of as being the degree 1 polynomials. So in this case, the degree 1 polynomials really correspond to cubic polynomials on P2. So degree 1 elements of C bracket P delta dual correspond to cubics on P2. And in particular, for example, if you take a general polynomial in degree 1 elements, you get a general cubic, and that determines a smooth cubic curve in P2. So we obtain smooth cubic or elliptic curve. It's often called in P2 from an equation summation AM, maybe I should say summation A BN, Z to the N1, where N ranges over elements of delta dual intersect N. Okay, so an elliptic curve is actually an example of a Calabi-Yau one-fold. So Badarev's statement, main theorem, is the following. so let delta dual be a pair of dual four-dimensional polytopes. I'm going to be specific about the dimension. His result is really much more general, but it makes me able to sort of state things precisely. And let X be of general hypersurfaces. So I have sum over M and delta intersect M, AN Z to the M1, so that equals 0. So I take such a hypersurface in P delta, and X check should be equal to summation N delta dual intersect N, Bn Z to the N1 equals 0. And that lives in P delta dual. So in other words, we have two hypersurfaces. I'm choosing them to be general, some general linear combinations of these monomials. I have one hypersurface in P delta, one hypersurface in P delta dual. Then these might be very singular because these toric varieties will in general be singular. Then there exists Claudial resolutions of singularities. X prime to X, and X check prime to X check, just as we had in the Green-Plesser construction. And with the flip of Hodge numbers, H11 of X prime is equal to H12 of X check prime, and H12 of X prime is equal to H11 of X check prime. So we get two Claudials with their Hodge numbers flipped as desired in mirrored pairs. Okay. So that's the better construction. And in many ways, this remains the gold standard for mirror pairs. It was very nice that this came out right after physicists told us about mirror symmetry and allowed us to have lots of examples to play with. In terms of lots of examples, if Philip Candelis gave a talk, he probably mentioned that already. This gives something like 400 million examples of Claudial manifolds. There's no shortage of examples here. There's higher dimensional statements, but they get more complicated. I don't want to go in that direction. But this is, this really, maybe from the point of view of mathematics, this was the beginning of the mathematical story of mirror symmetry. Okay, so should I just keep, Daniel, should I just keep on going till 5:30 now?
Yeah, I think you have 30 minutes more.
Yeah, okay.
And there is a question by Sahib.
I don't see.
Yes, sorry. Just wanted to quickly ask, your definition of polar dual, is it true that the double polar dual of a polytope is the polytope itself again?
Oh, that's
It's
right,
not...
yeah. So this is, this duality is reflexive, if you will.
Okay, thank you.
Yeah. I'm sorry, so good little exercise to check that. Okay, so that was, as I said, the first major milestone in the mathematical story of mirror symmetry. So the next milestone is something I'm not going to develop very much. I'm just going to say a few words about it, but this is one of the main threads of the study of mirror symmetry these days. And this is Conservator's homological mirror symmetry conjecture. So he tried to formalize a notion, and so philosophically, this is how I heard him put it many years ago. Mirror symmetry isomorphism between the symplectic geometry of X. And if you've seen some of this language from Whitten had an early paper where he talked about the A model and B model. This is often called the A model side. And the complex geometry of X check. So this is Whitten's B model. Now this is a very hand-wavy bit of philosophy. Symplectic geometry is about geometry of a manifold with a two-form, non-degenerate two forms, like a Kähler form, and studies things like Lagrangian submanifolds, which I'll introduce shortly. And to make this precise, he expressed it in terms of the Foucault category. On the A side, and the derived category the current sheaves on the B model side. So it was actually after Conservators announced this conjecture that the language of Dirichlet brains came in. These are essentially categories of Dirichlet brains, if you're a physicist and know what those mean. I don't want to say anything more about this because I'm not going to. I mean, this is a very important thread in modern mirror symmetry, but I don't want to go into this in any more detail than that. So this was, at that stage in 1994, was very much just a
Can I ask something?
Yeah.
Is this the most general statement of mirror symmetry?
So I think that's a slightly tricky question. In some sense, probably all forms of mirror symmetry can be expressed in this way, but usually I feel like that what this isomorphism should do is reflect some underlying geometry. So one can sort of ask what philosophically is the most fundamental description of mirror symmetry. And I personally view it more as that this should be a consequence of some geometric relationship between mirror pairs. And that's what I'll get to very shortly, the Sturm-Gauss-Aslow. Actually, I'm not sure if I'll get that far today, but I will talk about the Sturm-Gauss-Aslow conjecture. Okay, but that's not quite where I want to talk about yet. So the other sort of big milestone in mirror symmetry was Übenthal, Leon Yu Yao. I don't remember if it's 96 or 97. I think it was 97. And then many other people since have given simplified versions. They actually calculated a number of rational curves on the quintic of each degree, and verified the physics prediction. Okay, so up to this point, one had to view the Candelis sequence of numbers as being purely conjectural from a mathematical point of view. And they were able to actually calculate them and compare with what the physics predictions were. Now, this might be a slightly delicate point to say, but my feeling about this was that this was not really a mirror symmetry proof. So this proved that certain predictions of mirror symmetry were correct, but was not done by understanding what the mirror, quintic, was telling us about rational curves on X. Rather, it just proved that the formulas were correct. So this still left a question. Still leaves the question, as to why this works. Now, there's one aspect of this I want to go into, because again, this is going to be very important. So I'm going to turn back now to a more technical aspect of what's coming ahead. One of the key points is how do we define the number of rational curves of a given degree? So, before I just said, well, we count them, but that's really pretty subtle. So, for example, typical problem. In fact, if I take X to be the zero set of this Fermat quintic, this does not contain 2,875 lines. It contains an infinite number of lines. It contains 10 one-dimensional families of lines. So I was lying when I said it contained 2,875 lines. But what is true is if you deform X to a general quintic, the general quintic will contain 2,875 lines. But that's actually a fairly non-trivial statement. And you run out of steam. You can look at numbers of conics. Again, general quintic contains a number of conics, I said, but eventually it becomes very hard to show that the numbers really agree with precise enumerators counts on a general quintic. So you really need some more high-powered way of defining what these counts are. And this is through the notion of the realm of Witten variance. So here we want a way of defining a count curves which does not require deforming X. In particular, there are examples where if you really want to count curves correctly, you'll have to deform X away from being complex manifold, but all the way to almost complex manifold. And that enters the realm of those symplectic definitions of Witten variance, which I don't want to talk about. So rather, I want to sketch for you how we define Witten variance, how we define these counts inside algebraic geometry. So this is Koncevich's moduli space of stable maps. The notion of stable map is going to be a key one for us as we go forward over the next 4 lectures. So it's worth going through this carefully. So I'm going to fix a target space, let X be a non-singular projective variety. And then a stable map to X is a diagram. So I have C goes to X, goes to W, pi, along with sections P1 through Pn, and W to C with pi. such that, so we have several properties. First of all, C to W is a flat family. Don't worry too much what flat means here. As a flat family of, at worst, nodal curves. So in other words, i.e. Pi inverse of W, if you have a point. So let me write that more clearly. So we'll usually write a CW. So this is pi inverse of W. This is for W, the point in the base W, is a nodal curve. So what this means is a curve with some singularities. Might look something like that. But the singularities always locally analytically look like xy equals 0, like the crossing of two coordinate axes. So of course this can happen here too. So you have to look very locally. But that's what a nodal curve is. So every fiber of the map pi, every inverse image over the point is such a curve. So that's the first statement. Secondly, so P1 through Pn, what is it? Pn, yeah, are sections with disjoint images disjoint from the nodes. So if I were to draw this as a family, maybe I have a number of, here's W here, a number of singular fibers where the curve splits up into, develops some nodes. And then we have sections P1, P2, P3, which need to be disjoint and are not allowed to pass through the nodes. These are called the mark points. And then finally, we have the stability notion. So F is a morphism. Such that for each point W and W, the curve or the map F restricted to the fiber CW, along with the marked points P1 through Pn, has a finite automorphism group. And what's an automorphism of such a map? An automorphism of F is a map, isomorphism or automorphism phi CW to CW, and it should preserve the marked points. So phi pi is equal to pi, and it preserves the map F. So F composed of phi is equal to phi. Okay, so this group should be finite. The set of automorphisms should be finite. And actually, it's easy to check. So note this remark. This finiteness condition holds if and only if for each irreducible component on which, let's say, D CW, for which F is constant, either the genus of D is 0, and D has at least 3 special points, and by special points I mean marked points, nodes of C. The genus of D is 1, and D has at least 1 special point, or the genus of D is at least 2. Point being that curves of genus greater or equal to 2 always have a finite automorphism group anyway. Okay, so that's the notion of stable map, and this notion introduced by Concevic around 1994 is really the key one in this theory, in the enumerative theory of curves. It's been itself a big field. So now the main point here, so now we can fix a genus G, a number of n marked points, number n marked points, and a curve class A in the second homology of our target space. Then, sorry, I just saw chat come up, but it wasn't for me. So we have a curve class A and H to fix in. There exists a moduli space which is MGN of X A of such that the point in this moduli space corresponds to stable map F from C to X, or C P1 through Pn, just keeping track of the marked points to X, with C a genus G curve and the push forward of the fundamental class of C being equal to A. So this thing of A is giving the degree of the curve. Okay, so one of the important facts is that MGN, this moduli space, exists. Not quite sure who to attribute that to. There are many people working this in the 1990s, but MGN XA exists as a proper, i.e. compact, I should say compact, Dulin-Mumford stack. Now, I'm not going to assume that you know what a stack is, but just think of this as an orbifold, i.e. locally, it looks like a variety. Modulo finite group. Okay, so there is this object here. So for example, if we have X as general quintic, e.g. X is general quintic, one can show M00, so genus 0, no mark points, X, and then I'll write this as the class of a line, the homology class of a line in quintic. This consists of 2,875 points, corresponding to the 2,875 lines, right? So now we're, instead of thinking about the lines as being embedded, we're thinking about a map from P1 to the line, which will be an isomorphism. Okay, so I think that this would probably be a good stopping point. This doesn't quite finish the story of Gromov invariance, but then it would going to take a little bit more time to complete the story. So I think that's probably.
Yeah, I just want to mention that I just gave like 3 weeks ago a talk in Gromov, and then
Okay.
I tried to explain the physics side and the math side, so
Right.
people maybe they can go and watch there with more detail, and also for this homological mirror theorem by Concept H. There was a talk last week